Everybody, just want to welcome you to Module 1, Lecture 2 for ME 144 Heat Transfer. So in this lecture, we're going to be taking a look at Chapter 1, in particular Sections 1.1 and 1.2, covering the topics of heat transfer, looking at the physical origins and the rate equations. So as we jump into Chapter 1, the first thing we're going to do is take a look at some of the key definitions and phrases that we'll be utilizing within this chapter. So we'll begin by taking a look at thermodynamics and heat transfer. So thermodynamics is going to have to do with the amount of heat transfer as a system undergoes a process from one equilibrium state to another. This makes no reference to how long the process will take. But oftentimes we're going to be interested in this rate more than anything else of the heat transfer, as well as the temperature distribution within the system at a specified time. So a lot of this was what we're going to be asked within problems that we're solving, real life applications, things you might be doing for work. When we take a look at heat transfer down here, now this is going to have direction as well as magnitude. So in practice, we're often more concerned with this rate of heat transfer per unit time. So what is heat transfer? So we're going to take a look at an overview of the heat transfer mechanisms, where heat transfer is going to be defined as the form of energy transferred from one system to another as a result of a temperature difference between the two different systems. So heat can be transferred in three different ways. We're going to go over these in a little bit more detail in a bit. We're looking at conduction, convection, and radiation. So all of these modes of heat transfer are going to require the existence of a temperature difference. And all modes of heat transfer are going to go from the high temperature medium down to a lower temperature medium. So a brief overview and definition for heat transfer. This is going to be thermal energy in transit due to a temperature difference. Well, that leads to the question now, well, what is thermal energy? So thermal energy is going to be associated with the translation, rotation, vibration, and electronic states of the atoms and molecules that comprise the matter. So this represents the cumulative effect of microscopic activities and is directly linked to the temperature of the matter. So one thing that we want to be careful of is to not confuse or interchange the meanings of thermal energy, temperature, and heat transfer. So this is going to be important to recognize and understand the difference between all of these. So what I have here is a chart that we can reference back to kind of give us the definition for each of these here, along with the symbols and units. So if we take a look here, thermal energy is going to be the energy associated with microscopic behavior in matter. Symbols that we're going to utilize for this are U, capital U or lowercase u. And the units that we're typically going to see this in is joules or joules per kilogram. Next, we'll take a look at the term for temperature here. So temperature is a means of indirectly assessing the amount of thermal energy. This is the amount of thermal energy stored in matter. Symbol we use for temperature is capital T. Temperature units are typically in Kelvin or degrees Celsius. Again, we will see this in degrees Fahrenheit occasionally, so that's another thing to mention as a side note here, is as we're working through the problems, make sure you keep track of the units and do the conversions that are necessary. Now we'll take a look at the term for heat transfer. So heat transfer, as we mentioned before, is thermal energy transport due to temperature gradients. Taking a look at heat, heat is the amount of thermal energy transferred over time interval here, delta T greater than 0. Symbol here we use is capital Q in units of joules right there. Heat rate, we can see here, is thermal energy transfer per unit time right here. So the rate is per unit time. It's an easy way to remember that. Lowercase q is our symbol, and our units here are in watts. And last, we're going to look here at our heat flux. So heat flux is a thermal energy transfer per unit time and surface area. So the flux adds in surface area there. We're going to take a look over here. Our symbol is our Q double prime, and it's in units of watts per meter squared. So we take a look down the bottom here. U, thermal energy of a system. Lowercase u here is the thermal energy per unit mass of a system. So again, this is a great sheet to reference back to if you have any questions and understanding the difference between all of these different quantities here, or we want to take a look and see what units we should be in, or if we're going through a problem and we need to know what symbol we're using within it for each of these quantities. This is a great slide to reference back to. Now we're going to take a little bit of time and look at the modes of heat transfer right here. So a couple examples here. So we can see in this first example on the left over here, we have conduction through a solid or stationary fluid. Now, the things we want to know, we've just talked about some of these symbols in terms, so we can see here's our heat flux going through this solid right here. We can see our surface temperature over here denoted by this little dot with a line going up to T1. So that's the surface temperature on this left-hand side surface there. T2 is the surface temperature on this surface over here. And we can see in this diagram, they tell us that T1, our surface temperature on the left side, is greater than our surface temperature T2 on the right side over there. So this was our conduction example there. Next, we go to the middle here and we can see convection. So this is convection from a surface to a moving fluid. So we can see we have a moving fluid here, temperature T sub infinity right there. We can see our T sub S, so our surface temperature is greater than our T sub infinity or our moving fluid temperature right there. We can see our arrows indicate that it's moving over in this direction right there. There's our Q double dash there, or our heat flux there, and here is our surface down here and our surface temperature given to us as our T sub S. And the last example we'll take a look at here is radiation. So the net radiation heat exchange between two surfaces. So we can see in this diagram here, we have a top surface here, we have a bottom surface over here. The surface here, we're going to call our T1 surface temperature is T1. Our surface down here has a surface temperature of T2 right there. And you can see the top surface here has a heat flux of Q1 double dash and a heat flux down here for surface 2 of Q2 double dash right there. So now let's take a look. What is the real difference between conduction, convection, and radiation? So if we're talking about conduction, conduction is heat transfer in a solid or stationary fluid, gas or a liquid, due to the random motion of its atoms, molecules, or electrons. Whereas we talk about convection, convection is heat transfer due to the combined influence of bulk and random motion for fluid flow over a surface. So we saw that there. There's our fluid flow up top. There's our surface right there. And then lastly, we'll take a look at radiation. So radiation that is emitted by matter due to the changes in the electron configuration. So energy that is emitted by matter due to changes in the electron configurations of its atoms or molecules and is transported as electromagnetic waves or photons. So a little bit more on the differences between these here, where we have conduction and convection. This is going to require the presence of temperature variations in a material medium. When we're talking about radiation, although radiation originates from matter, its transport does not necessarily require a material medium and can occur most effectively in a vacuum. I think another great way to understand the difference between conduction, convection, and radiation is to take a look at this image here. So we have a visualization of all three of these modes shown in this image here. So if we're talking about conduction right here, we can see we have this solid object. So there's our solid piece right there in the definition for conduction. So here's a metal fire poker right here, a metal rod that we're holding on to. And we can see that it heats up. Here's your temperature down here from this heat source or our fire here. And this heats up the metal rod there by conduction there. Now, if we're talking about convection, now we have this fluid flow that we can see through the air right there off of the same fire going up, and we can feel it on our hands up here. In radiation, we're a distance away without the fluid flow, and we can still feel the heat source back here on our hands. So I think this is a great way to understand the concept between the three different modes and visualize it there. Conduction, the solid piece right there, convection, fluid flow, and radiation, a distance away without the fluid flow there. So as we jump into some of our math here, take a look now at our heat transfer rates. Let's talk just about conduction right here. So this is a general vector. We can take the form of Fourier's law here, so we can reference back to our textbook for this. We have our general equation for Fourier's law here. We have our heat flux right here in units of watts per meter squared. And this is going to be equal to the negative K value here, which is our thermal conductivity in units of watts per meters times Kelvin, times our delta T over here, which is our temperature gradient, and this can be in units of degrees Celsius per meter or Kelvin per meter right there. Next, we're going to take a look at the application right here. So an application right here, we're just going to do a simple 1D steady conduction. This is going to be across a plane wall of constant thermal conductivity. So a very simple case right here that we're going to be dealing with. So if we look at this as kind of a 2D object down here, you can see we have our length over here going in our x direction over here. This is just going to be our surface temperature, so we can break this 2D visualization down into a 1D problem right here as we're going across this here. So there's our surface temperature T1 on this side. We come over here some distance L away, and we have our surface temperature over here of T2 right there. And we can see here is our heat flux right here coming into our plane wall. So in order to calculate our heat flux, we can go back up to Fourier's law up here that we just went through here, and we can see that our heat flux is equal to our negative K times our delta T. So our delta T is our temperature gradient, so change in temperature with respect to distance. Now we can see here our distance here is going to be in our x direction, so it's dt dx. Now we can plug in for that there. Our dt is our change in our temperature. So our temperature change is T1 and T2. So we can see it's a T2 minus T1, our surface temperature change right there, all over our dx, or our thickness here, the distance that we're traveling in our x direction, which we can see from our diagram is going to be our L. So we can take Fourier's equation here from general form, comes down now here that our heat flux is equal to our negative K, or thermal conductivity, times our difference in temperature from surface T2 minus T1, all over that width there, or that length there, L, right there. So this simplifies down to this equation 1.2 from our textbook here, that our heat flux is equal to K times T1 minus T2, and you can see I just distributed that negative value there to flip those around like that, all divided by the thickness down here of our wall here, L. Another note down here, if we want heat rate from our heat flux, we can go back to that definition page that I talked about there. We can see our heat rate is given in units of watts. We can do our unit analysis to double check this. We can say, okay, if we take our heat flux times our area here, we double check the units, that will give us our heat rate right here in the correct units of watts. So now if we continue on with our heat transfer rates, but now looking at convection, this is going to be the relation of convection to flow over a surface and development of our velocity and our thermal boundary layers. So if we look at this diagram down here, take a look at the main components first, and this is something that I want you to always do, even as you're solving problems for homework, example problems, or exams, is to really take a look at the diagram and try to understand everything that they give you in it. So in this course here, a lot of information can be inferred from this diagram that may not be given in the problem statement. So if we come down here, the first thing we notice, okay, we have the surface down here, and they tell us that this is a heated surface right there. We can see we have some fluid flow going from left to right over the top of this here. And we can see we have our velocity distribution given to us on the left and our temperature distribution given to us on the right, where we have this distance y, where y is going to be the distance away from the top surface right here of our heated surface going up and away. So if we look at this here and we talk about our velocity on the left side, if we go up a distance y away from this heated surface, we can see our velocity is going to change as we go up further away from the surface. And we can see it's going to increase as we get further away. So this would give us this function here, u of y, or our velocity as a function of distance away from our heated surface. Now we go over to the right here and we have our temperature distribution over here, our T of y. We can see here as we go up in the y direction here, further away from our heated surface, our temperature right here is going to decrease in this direction here, like this, following that curve there. So we have our surface temperature of our heated surface, T sub s. Our T sub y is going to be a function of this distance away, our y distance away from that heated surface. So if we come down here, the next thing that we want to look at is our governing law when we're dealing with convection and heat transfer rates. And this is going to be Newton's law of cooling. If you think of that, that makes sense. We have a surface, it's going to be cooling as we move a distance away, y, from that surface. So this here, we can see our heat flux is equal to our H value here times our temperature difference between our surface temperature and our ambient temperature, T sub infinity. And this comes from equation 1.3a in our textbook, where our Q double prime is our convective heat flux. And here's our units right there, watts per meter squared. And H term that we're now seeing here, a new term here, is the convection heat transfer coefficient. It has units here of watts per meter squared times Kelvin. Now, as we continue on with our discussion of heat transfer rates, we're going to look at our last mode right here, our radiation mode here. So if we're talking about radiation here, our heat transfer at a gas surface interface for radiation is going to involve radiation emission from the surface and may also involve the absorption of radiation incident from the surroundings, our irradiation, our term here G, as well as convection here if our T sub s, our surface temperature, does not equal our T sub infinity of our surrounding temperature there. So we're going to take a look at our governing equations here. If we're going to discuss our outflow due to emission, we're going to reference equation 1.5 from our textbook here, where E is equal to our epsilon E sub B, which is equal to our epsilon sigma T sub s to the fourth. So let's break this down and look at each individual component, what it means, its units, and how it relates to that governing equation there. So our E here is going to be our emissive power, and this is going to have units of watts per meter squared. Our epsilon here is going to be our surface emissivity, which right here, this is going to be in a range between 0 and 1. Our E sub B here term is going to be our emissive power of a black body, or our perfect emitter. And our sigma here is going to be our Stefan-Boltzmann constant, which is given to us as a value of 5.67 times 10 to the negative 8 watts per meter squared times Kelvin to the fourth for our units. Now, if we talk about this second part right here, absorption of radiation, the energy absorption due to irradiation here is going to be our G ABS is equal to our alpha times G there, which is equation 1.6 from our textbook. Breaking this equation down, looking at the individual components as well, this is going to be our absorbed, so our ABS stands for absorbed here, incident radiation in units of watts per meter squared. Our alpha is our surface absorptivity, which is, again, still between 0 and 1 for our alpha term there. And G is our irradiation in units of watts per meter squared. So we can take a look up here at our diagram up here, and what we can see, there's our surface right there. There's our heat flux right there. We can see our E value for our emissive power right there. We can see our G value right here for irradiation right there. We have our surrounding gas with its temperature and our H value there. So this is surface emissivity, our epsilon right here. Absorptivity is our alpha, and our surface temperature here is given to us as T sub s. So this is typically what we could see for an example problem or a homework problem right here if we're talking about radiation. And again, as a quick overview, our governing equations here, if we go back to 1.5 right here for our emissive power equation, and 1.6 right here for our radiation or near radiation equation right here for energy absorption. So we briefly mentioned irradiation. Let's take a look at that in a little bit more detail right here. So this is a special case of surrounding surface exposed to a large surroundings of uniform temperature, which we're going to show here as our T surround right there. So we can see right here, here is our surroundings of a very large uniform temperature right there. There is our T surround of that right there. Here's our surface down here. We can see we have this relationship that we've seen on the previous page right here. For G, our irradiation is equal to G surround is equal to our sigma T surround to the fourth. So we can see I have our heat flux here, our radiation and convection right there. Gas in our surrounding area right there with our T sub infinity and H values there. So this is our surface of emissivity. E is equal to our epsilon is equal to our alpha term there. Area is given to us as A, and we have our temperature here of our surface right there of our T sub s. So if our alpha, as was shown here, is equal to our epsilon, then our net radiation heat flux from the surface due to the exchange with the surround is given to us by the following relationship here, which if we reference back to our textbook, this comes from equation 1.7 in our textbook here. We have our radiation heat flux here is equal to our epsilon E sub B times our T sub s minus alpha G is equal to our epsilon sigma times, now this temperature difference right here between our T sub s to the fourth and our T surrounding to the fourth, or T sub s, if we recall, is our surface temperature, and our T surround is right up here. So quick note down here to remind us for all of the individual terms within our equation here. Our E sub B is our emissive power of a black body or our perfect emitter. Our G is our irradiation in units of watts per meter squared. Our alpha is our surface absorptivity of alpha value right here between 1 and 0, and our epsilon is our surface emissivity between 0 and 1 as well. Now, something to note within this as well is if we're doing a problem, solving a homework problem, example problem, this is a great thing to do. We're going to have our governing equation. So this is our governing equation. We can tell where it came from. So even if you're solving a homework, it's really nice to say, okay, I'm using equation 1.7 from my textbook. This is why I'm using it, and this is how it relates down here. And with this here, I like to write this all out. And you can see this as I go through some of my example problems later on throughout the semester. I have my variable name, what it physically is, and my units. And the other thing that I would have here, if this is an actual problem, was the value assigned to it either in the problem statement or given in our initial diagram. So I can quickly reference back and plug right into my governing equation from all this information that I already have readily available and written out in my solution. One thing that we'll also know as we're going through and solving problems is there's not one direct method or only one solution for all our problems. There's going to be different ways to solve these, different governing equations we can start with. And here's an example here. So ultimately we can go with equation 1.8 from our textbook here, where we have our heat flux from radiation here is equal to this relationship here of our HR times T sub S minus T sub surround right there, where HR takes the place from equation 1.7 for the other terms there, and this is our radiation heat transfer coefficient. Our units are in watts per meter squared times Kelvin. So as a side note here, unit analysis is going to be one of your best friends within this course here. So how do you know you can use this instead of something else, or use this governing equation instead of another governing equation? Does it still give you the right answers? Well, you know what your final answer units should be in. We can reference back to that slide that I gave earlier at the beginning of this lecture. We know, okay, our heat flux needs to be in these units. If I do my unit analysis out, does it double check? Do the units come out correctly? So that's always a good thing to do if you're not quite sure if you can substitute in one term for another term or use a different governing equation within your solution, is to go back to that unit analysis. So I will encourage you in all of your problems, whether you're just working through example problems on your own or turning in homework problems, to really write out your units and do that unit analysis. It's going to help you in the end. So HR here is equal to that term right here of our epsilon times our sigma value right here times TS plus T surround times our TS squared plus our T surround squared. And this comes from our equation 1.9 in our textbook right there. So if we have combined convection and radiation here, we now can see that our heat flux is equal to convection, our heat flux due to convection, our heat flux due to radiation right there, summing those together. So we can sum all this right here together now, and we have our H value times our TS minus our T infinity right there, plus now this HR, so this comes from this equation right here, times TS minus our T surround, and we can see that we're just adding these two terms together there, and now we have this new equation here, which relates back to equation 1.10 in our textbook. So one thing that I think is a little bit challenging within this course is to identifying the processes for a physical system that you may be doing. And this is something also to think about as you're working on your group projects as well. We really need to understand, okay, what am I dealing with? Am I dealing with convection, conduction, radiation? What surface am I dealing? What are my two temperatures that I'm looking at? So this is a great problem, again, to keep in your arsenal and reference back to right here. So we have in this diagram right here, we have some ambient air outside, we have a heat source, and we have an inside room right here with its own temperature there as well. And what we have here is a single pane and a double pane window. So we can break these apart as individual single pane and double pane and try to identify the process for each of these right there. So let's just take a look at the simple case right here, our single pane at the bottom right there. Now down here, the bottom, I've written out all these terms right here so we can reference back. So again, this is a great slide to reference back to if you're trying to understand, okay, what temperature, is it radiation, convection, conduction, all of those individuals there, and how does it relate to the physical diagram that they give us there. So we can take a look right here. We have our Q sub S coming in at the single pane. Right here, there's our single pane window again right there. We come down here, our Q sub S is our instant solar radiation during the day. Fraction transmitted to room is smaller for the double pane. So that's just a little side note right there. So this is our Q sub S, so our radiation right here coming in from our sun through our single pane window. So there's our Q sub S term right there. Now we can take a look on, we can see, okay, we have our Q convection 2. We can come down here, our Q convection 2 is convection from the outer surface of single or second pane to the ambient air right there. So this is going from the pane to the ambient air. We look at this here. Yes, that's coming from the pane to the ambient right there. There's our convection 2, Q convection 2. Now we'll look down here, Q radiation 2. Here's our radiation term right here. So we come down here right now and we say this is our net radiation exchange between the outer surface of the single pane window right here and the surroundings right there. So there's our surroundings right there. So this is our radiation term right there, our Q2 right there. So now we've dealt with our single pane on the outside of it. Let's take a look at the inside of our single pane window right there. We'll start at the top up here. We have our Q convection 1. So we come up here, our Q convection 1 is convection from the room air to the inner surface of the first pane. Does this make sense? Absolutely. There's our room air right there. There's our surface right there of the single pane. Perfect. Now we'll go down here to conduction term right here, our Q conduction 1 right there. We can see is a conduction through the first pane. So we can see this is going through, conduction is going through right there. Absolutely. And last, we have our Q radiation 1 right there. So we come down here to our Q radiation. Now this is a net radiation exchange between the room walls and the inner surface of our first pane right there. So there's that term right there. So now as we're dealing with double pane, it's going to get a little bit more complicated, but if we think about this as almost two separate systems that are combined together for this double pane, then it makes sense. You can see you have your outer pane and you have your inner pane right there for this double pane window right here. So you're going to have another process occurring between those two panes. So there's your QS acting on this outer surface of the outer pane right there, which again is that incident solar radiation during the day coming in there. Then you have your Q conduction 2, Q convection 2, and Q radiation 2, which we've already discussed before. The only difference is you can see over here we had convection and radiation. Now we also have a conduction term going through this guy right there as compared to when we're dealing with a single pane right there. So then we can take a look at the inside pane, inside surface of our outer pane of glass for the double pane right here. And we can see we have our Q convection S here. If we come down here, this is the convection across the airspace between the two planes. So that's the difference here. Now with this air gap between the two panes, which helps with our insulation. And now we also have our Q radiation S term right down here, which is the net radiation exchange between the outer surface of the first pane and the inner surface of the second pane. So the outer surface of the first pane and the inner surface of the second pane right there. Then we go back over to our inner pane right here in our double pane system, and you can see we have our Q convection 1. So if we come back over here to our Q convection 1, this is the convection from the room to the inner surface. So there's a room to the inner surface. Our conduction 1 right here, which is conduction through this first pane right here, and our radiation 1 right there, which we've already discussed there, which is going to be our net radiation exchange between the room walls and the inner surface of our first pane right there. So again, this kind of goes through the difference between single and double pane and talks a little bit about this air gap in between when we're dealing with a double pane window, and it threads it all back to our physical problem right here. So a lot of times it's great to have both of these diagrams, a physical diagram to really understand what's going on in real world terms for our problem right here. So we have this here, but then we also have the schematic, which is very important. It can help us when we start plugging into our governing equations and need to understand, okay, how does convection, radiation, conduction for each of these surfaces relate? Where do they plug in with my indices and my variable names within my problem and my governing equations?